Hello, welcome to SQL Bits. My name is Pedro Lopes. I'm a program manager in the Azure Data SQL Server team, and my session today is everything you need to know about storing strings in SQL Server and Azure SQL Database. And there's a lot more than meets the eye here. The information that we're going to share today will allow you to make decisions about database design for years to come to support multilingual applications in your database systems. So, storing strings, why would you care about that? A string is just a string, right? Yes and no. There's a lot more than meets the eye, like I said. Let's use the example of the Contoso company. They have been based in North America for many years, and their customer base is typically from Mexico, Canada, and the United States, which means that they typically have to deal with three major languages: Spanish, French, and English. Let's think through the challenges that this customer may have, this company may have, when handling languages. Storing data in multiple languages in a single database is a difficult proposition. You need to make sure that you select the code page that can represent all the characters from all the languages that you're trying to store. And a code page is a representation of both the character set, meaning a specific subset of all the known characters that are specific to that language, but it also sets how the characters get encoded, how a character set gets mapped into bytes. And code pages are set by the operating system. When you select the language of the operating system, you are selecting a code page. And that code page is impacting all the applications that sit on top of that operating system, such as SQL Server. When you select a collation that is setting a specific language, you are inheriting the behaviors of the underlying code page that's set by the OS. So let's go back to the Contoso company. They have been set for many years with customers only from North America, Latin alphabet, everything is fine. However, later the company expands to parts of Asia and Eastern Europe, and now the same database must start storing customer names and addresses from Russia, China, Japan, and other countries, which have a different alphabet. They don't use the Latin alphabet, which means that the character set that's attached to the code page that was chosen for the database no longer suits them. Here are the new challenges for Contoso. They need to find a code page for the database that can store all the required language-specific characters that they now are onboarding. That's difficult in itself. They will also need to guarantee that, let's say they go with a design where they have multiple tables, one for each language, and that means that also they will need to change the application, which is a problem in itself. But let's say they do that, and now the application needs to join data from these different tables. These tables have columns with different collations. Obviously, they need to represent that specific character set. And when you join data to send to the client application, you need to ensure that there is a correct translation of all the special characters from each of the code pages, and you're not generating garbage, gibberish, because gibberish means data loss. If you use that result set to then store in some other table and you're storing gibberish because you couldn't translate characters correctly, you have data loss. If you are presenting gibberish to the client application, you have data loss. So it is very important to think about the concept of a code page when you think about what you may potentially store as strings in your database. So their requirement is ultimately to provide a global multilingual database to all the applications and services that Contoso now has to deal with. And databases that support international clients should always use Unicode capable data types instead of non-Unicode capable. And we'll see more into this for the rest of this session. So what is Unicode? Think about Unicode as being something unlike code pages that set both the character set that they're capable of and how to encode the data. Unicode decouples these concepts. Unicode is simply is just the character set that can be represented for any given language, and the character encoding is a different concept. We'll talk about that concept in a few minutes. Unicode can represent the entire repertoire of known characters to man from every language, including emojis, including musical characters or mathematical symbols, everything. In other words, it's the universal character set. It's a standard to map code points, which means the ordinal position of each character in the entire UCS array to characters that can be read by the human eye. It's over 1.1 million characters that can be represented, and those include both visible and non-visible characters. For example, if I use the ASCII function to retrieve the Unicode value for the uppercase P, I get the value 80. If I then take the value 80 and use the char function to return the character that is that maps to that code point, I get the uppercase P. Similarly, with the Chinese character you see in the bottom query there, if I use the Unicode function to retrieve the code point for that character, I get 26,481. And conversely, if I use that as a parameter for the nchar function, I get the character that I had. So this is what Unicode sets. It sets a positional, it sets a position for the character in the entire repertoire of UCS. And how does it encode? Well, there are different encoding schemes for Unicode. UCS can represent everything, all the characters, and UCS2 can only represent the first 65,536. It's called also the BMP, the basic multilingual plane. Characters that fit in this interval will use 2 bytes per character, or 1 byte pair. And up until SQL Server 2012, this is the character set that SQL Server could represent, could store, UCS2. UTF-8 is another form of encoding for Unicode. This can represent all the UCS repertoire, so all 1.1 something million characters. And it's the most popular. We'll see how it's actually mandatory for some systems in the EU and Japan, for example. And then there's UTF-16, which is the evolution of UCS2. It can also represent all characters, and it's also variable with encoding just like UTF-8. But instead of being measured by just bytes, 1 to 4 bytes, like UTF-8, it is measured in byte pairs. So it can be 1 byte pair or 2 byte pairs per character. And why choose UTF-8? It's about maximum compatibility. It's actually a requirement for many countries, for many regions, and you see a few examples here on the screen. It's just ensuring that you have maximum compatibility when moving data from system to system if you know that they're encoded into UTF-8. So let's look on string encoding in SQL Server, the engine. Up until SQL Server 2012, like I said, all that SQL Server could encode in string data types was at most UCS2, so the first 65,536 characters of the entire Unicode repertoire. Encoding in strings in SQL Server is a mix of using the right collation with the right data type. As you see here, in SQL 2012, we introduced the concept of supplementary character collations, the suffix _SC, as you see there. A collation that has that flag is signaling to the engine that if I'm using this collation with this data type, in this case nchar and nvarchar, you will encode in UTF-16. If you are using any other collation that is not compatible with supplementary characters, then you are encoding in UCS2. In any of these cases, if you're using the char of varchar data types, you are only encoding using the code page, which we've already alluded that can be a problem for multilingual databases. And you see here a few examples of collations that are compatible with the supplementary character, and you see that is a suffix SC in most of them. The newer collations that have the 140 in their makeup string, those are already intrinsically SC capable. So even if you don't see the SC suffix, 140 collations already automatically support this. Starting with SQL 2019 and in Azure SQL Database, we introduced support for UTF-8. It is still a combination of data type and right collation, but some things have changed in this sense. If we are using a UTF-8 suffix in the collation, that means that when you're using char and varchar data type, you are now allowing the engine to encode your data in UTF-8. If you are using nchar and nvarchar, nothing changes. Even though you're using a UTF-8 collation, the combination with that collation with the data type nchar and nvarchar will still encode in UTF-16. Here's a few examples of UTF-8 collations. You see that by adding a suffix UTF-8, you get the capability of using UTF-8 encoding with a char varchar data type. If you want to know the collations that you have available in SQL Server that are UTF-8 compatible, you can use the query here on the screen. Basically, all Windows collations that are supplementary character compatible have a UTF-8 counterpart. So you are all set there. How do data types relate? As I mentioned, we choose the combination of the right data type with the right collation. Now, think about how that works. Data types have always been encoded in the same way, in the sense that, okay, if I'm using nchar and nvarchar, I'm using 2 bytes per character, which means that an nchar 20 is 20 characters. And the char or varchar uses 1 byte per character, so char 20 is 20 bytes, it's also 20 characters. That's actually not true. There is a myth that anyone that works mostly with Latin alphabets, with Latin characters, kind of fell into that trap. These data types, the integer number, expresses a number of bytes or byte pairs the data type can represent. When you enter the realm of Unicode and variable width encoding with UTF-16 and UTF-8, then you really need to look upon the data length, so the amount of bytes that you're going to use for your string, and not the number of characters. Someone that's used to working with non-Latin alphabets, so folks that work with data from China or Japan or some other East Asian country, they know this already. But this is a myth that has been created for the Western hemisphere, if you will. What are the storage differences between UTF-8 and UTF-16? Let's look at just 2 examples. The ASCII range, which is from 0 to 127, can represent most of the characters in Latin alphabets. If you look at the storage aspects of this, you see that UTF-8 will be able to store each character of the ASCII range using just 1 byte, whereas UTF-16 will use 2 bytes. If you go to the 3rd line there, Chinese, Japanese, Korean, you see that for that range, so the upper range that goes all the way to, that makes up the BMP range, so the basic multilingual plane, you see that UTF-8 we actually start using 3 bytes per character, whereas in UTF-16 we will still use 2 bytes per character. That is important for decisions that we need to make later. This demo, which you can get at that URL right there, will show you in a SQL notebook exactly what I'm talking about in terms of debunking that myth that we have in the West about the data types and number of characters. So which one do I choose? Let's look at some performance and operational considerations between choosing UTF-8 or UTF-16 to store our Unicode strings. Let's look at storage and performance. This is according to tests that we've done. If you know that your data set primarily uses ASCII characters, so majority of Latin alphabets, you'll probably want to choose UTF-8. You'll get 50% storage savings, we've seen that. An nchar 10 will require 20 bytes of storage, whereas a char 10 requires only 10 bytes for the same Unicode string. We have tested that when doing intensive read-write I/O between UTF-8 and UTF-16, we measured an improvement of around 35% when using UTF-8 and when we're using both using cluster tables with 1 non-clustered index on the string column. When compared to a heap, again, UTF-8, UTF-16, we saw 11% improvement. So it's an improvement all around, and it is our recommendation for you to use UTF-8. If your data set is predominantly extended Latin, and also these other languages, both UTF-8 and UTF-16 use 2 bytes. So performance measurements that we've seen are very similar, and you can choose whichever you want to. If your data set is primarily Chinese characters, Japanese, Korean, so all the other characters that sit in the BMP range, then you will want to use UTF-16. And that's because UTF-8 in this range will use 3 bytes per character, and we measured about 25% degradation, again on intensive read I/O, when comparing one to the other. So definitely you want to go with UTF-16 here. And if you are primarily storing characters in the upper range, such as emojis or musical symbols or mathematical symbols or other such characters, then either is fine, because both UTF-8 and UTF-16 will use 4 bytes per character. A few other performance considerations. When you're doing compute-intensive operations such as sorts or merge joins, we've seen that UTF-16 is generally marginally better than UTF-8 for the same data set. And this has to do with some internal conversions that we have to do during these operations. For hash joins, like or inequality comparisons, these perform slightly better in UTF-8, again for the same data set. And you have other considerations such as UTF-8 being able to be set at the database level. Now, for existing databases, you set UTF-8 collation for the database, but if you already have objects in there, tables obviously with columns, then only new objects will be created in UTF-8. Existing objects must be converted, and we'll have more about that in a little while. UTF-8 and non-UTF-8 can coexist in the same database. There's no problem. You can have one table that is UTF-8 and one table that is not UTF-8, and you can use the collate keyword to kind of make sure that you don't have data loss in terms of comparisons when you are doing joins, for example. Now, here's a tip. Always measure your character data length, not the number of characters. We've seen that's a myth, especially for Western languages. Data length will measure the encoded storage bytes. So you will know how many bytes you can store in a char20. You know that you can store 20 bytes, but you know how many, if your string fits those 20 bytes or not. The len function measures the number of characters, so it's not very useful in this perspective. In the SQL Server Tiger toolbox, we have a script that will allow you to look at the current database and determine whether you are better off using UTF-8 or UTF-16. So do leverage that. Note that UTF-8 is not supported with XML data type, in-memory LTP, or always encrypted when using enclaves. If you are using always encrypted without enclaves, it is fully supported. Think also about string literals. If you're declaring strings that do not have the n prefix, those will be encoded first in the current collection of the database before being set by the collate keyword, for example. In other words, if I have a database that has a code page set, and then I have a table created with a column that's set in UTF-8, if I need to convert that data, I will go only first through the code page and then through the collation set in the collate keyword. That may mean data loss if the code page of the database does not cannot comport all the characters. So do use Unicode literals instead of normal string literals right there. We have this documented. Another demo for you, a couple of notebooks that will explore this performance characteristics that I mentioned. They're also available in that URL you see on the screen there. I urge you to go and look at it and run the demos for yourself, or just look at the results already stored in the SQL notebook. Now, conversion methods, how to move from UTF-16 to UTF-8 if you need to. Imagine that your column data is encoded in UTF-16 if it's non-Unicode. It's a normal char or varchar, and you were not using a Unicode. So think about these two tables here, and I can see that in the top one, I have n varchar data type. In the bottom, I have a varchar data type. In the top, I have a supplementary character enabled collation through the SC suffix, and not in the bottom one. I can convert in place doing an alter table. It's easy to implement, but it's possibly a blocking operation. So if you have your application working, it may pose an issue in terms of blocking. And if you have a large table or busy applications, that will be a problem for you. You can copy and replace. It's much faster than in place. You create a table on the side, move all the data, and in the end, you delete the old table and rename. This is much faster to do, but handling complex schemas that have dependencies such as foreign keys or primary keys can be a problem there. So I'll leave you with some resources you can go and explore. This, for example, has the UTF-8 documentation and demos right there, and a few others. I urge you to go and read more about this and enjoy the rest of SQL Bits.